All right, so I want to welcome everybody again to tonight's webinar. This is on the November 13th tornado outbreak here in southern New England and on Long Island. I'm Joe Deli Carpini, the Science and Operations Officer, and joining me tonight, Hayden Frank, one of our lead meteorologists, and Rodney Chai will be with us, one of our meteorologists as well. So I'm going to start off by handing it off to Hayden, who's going to take us through an overview and some of the model data and the mesoanalysis. So Hayden, take it away.
All right, great. Thank you, Joe. Well, this was quite an event. We had 11 tornadoes touch down on Long Island, Connecticut, into Rhode Island. They were pretty much all week, 9 EF0s, 2 EF1s. These were actually the first tornadoes on record for the month of November in Connecticut and Rhode Island. Keep in mind, the technology, which we'll go over in a bit with the radar, the use of social media, people's knowledge of meteorology in terms of being able to pick up these signals from not only the meteorologists, but folks in the field, has helped us identify more of these weak tornadoes that maybe 15 or 20 years ago might have not gotten back to us. We wouldn't have known about them, or maybe it would have gone down as, straight line wind damage. But that's just a replica of the increased technology and all the tools we have, which we're going to go over. The tornadoes were in a classic environment for fall tornadoes, low instability, but very high shear. We'll talk about that more. And there were some real big surprises. Dew points were only in the low 40s, not something that would stand out for thunderstorms, let alone tornadoes. So we're going to kind of dissect that a bit more and go into some of the things called the CAPE, which we look at not only the total CAPE, but the CAPE in a particular part of the atmosphere, along with the amount of shear, the turning of the winds in, say, the lowest part of the atmosphere. And believe it or not, there was actually some snow at the time across far western Mass while the tornadoes were ongoing across Connecticut and Rhode Island. So we'll go into what exactly happened. Well, this is a list of all the tornadoes that occurred that day. Obviously, they were fortunately weak, short-lived, but they did do damage. We were mainly looking at, tree damage, the typical things you would suspect from weaker tornadoes. And you also keep in mind that these tornadoes occurred fairly close to the coast. And it may be counterintuitive, but I think there was a reason that they did occur near the coast. And we're going to discuss that as we go through the presentation here. So November in tornadoes, obviously, these were the first on record, going back in for Connecticut and Rhode Island, going back to 1950. But across Massachusetts, they're extremely rare too. There's only been 2 on record, one in 1967, and then another cluster there in November 7th of 1971. But those are the only 2 dates for Massachusetts. And then tornadoes in New York, obviously they're rare as well. I mean, there's a few instances here in the late 90s and 2000s. And like I said, with these weaker tornadoes, I don't think it's a coincidence that you're seeing them more in this time frame, as the tools we have, the spotters in the field have really helped us identify these events. Now, you'll see one listed November 16th, 1989. That was actually a huge outbreak of severe weather, more like almost like a summertime, springtime type of setup with severe weather from the southeast right to the northeast. There were actual tornadoes across the mid-Atlantic into the northeast, and unfortunately there were fatalities from that event. And that was actually followed by a Thanksgiving snowstorm for the I-95 corridor. So 1989 November was quite an active month in terms of severe weather and also winter weather. So these are look at the damage photos. As you can see, a lot of downed trees, some on houses. There were power outages. Fortunately, no fatalities, no injuries from this event. But obviously, you could see there's fairly significant tree damage in the path of those tornadoes. So was fortunate that we did not have any injuries from this event. So what we're going to do now is I'm going to go into the model data, then we're going to go into like a higher mesoanalysis event review, and then I'm going to turn it over to Rodney, who's going to go into the specifics of the radar signatures, which were really, really subtle. And you can expect that in this type of event. So one of the things we as forecasters tend to look at when we're coming on shift, and I know I like to do it, especially, if I'm looking for, say, is there going to be any significant events? Is there something, that might stand out? Well, this is called our situational awareness table. And it's basically looking at a model climatology. The model's basically looking at itself with the current data and seeing, well, how does it fit inside, say, the 30-year climatology of the model? And where you see like 99, and especially where you see those reds where it's maxed out, that means it's outside the model's climatology. That means that event being reanalyzed, the model recognizes as something that it hasn't really seen before. It's above those thresholds. So when you have something like that, that is what we call like a red flag for a potential significant event. It doesn't mean that's going to happen. It's just kind of a signal to forecasters, and it can kind of get you to focus in on a particular event. What you'll also notice here is the max thing was actually on Friday, the 12th, not the day the actual tornadoes occurred, which was on Saturday. So this can signal things. It doesn't necessarily mean it isn't or is going to happen. It's just one of those things to look at. If you remember the day before, the reason that was maxed out, the V, and that's looking at north-south component of the wind, we had strong winds that day, 30 to 40 mile per hour, sustained winds with some gusts over 50. We also had 2 to 3 inches of rain, so there was some street flooding. And you see the PW, that's kind of an indication of the amount of moisture. You see those higher values, that you get higher values with stronger winds. That's definitely potential for a significant rain event. But the actual severe weather event, this table wouldn't have really led on to that. You'd had to look a lot more details, which we're going to do here in a bit. So one of the things we also like to do is look at these SIPS analogs to start off our forecast process. And basically, it's looking at what the model is forecasting, and then it's going back into the CLIMO and say that you have a similar setup. Has there been severe weather with this type of setup? Has there been winter weather? Has there been flooding? Well, sometimes that can let you in on, hey, this happened quite a bit of times. We had hail with this, or we had wind, or we had tornadoes. In this case, it didn't really pick up on anything. And again, that doesn't mean anything that it's not going to happen. It may be just because it's such a rare event that there was really nothing to compare it to. So again, this is just a tool to utilize. It's not a golden bullet to tell you what direction to go, but just something that can get your mind thinking, hey, I may have to look out for this if I wasn't thinking about it. Okay, so we're going to go on to the HREF, and that is a model that the forecasters like to use here. I like to use it a lot myself. It's kind of several of our high range models put together. And when I say high, I should say high resolution. So these can pick up on specific details. And what you'll notice here is a big shortwave trough with very strong winds at 500 millibars, actually in excess of 100 knots. And that is what you're going to normally need if you're going to get, say, an out-of-season severe weather event. You're going to be lacking the instability. So you need to compensate for that somehow. And the way you do that is with very strong wind fields aloft. And that was one part to the puzzle. Now, this was another part to the puzzle. This was right around the time of the tornadoes, valid at 5 p.m. This is the HREF. It is a 22-hour forecast, so it's valid 22Z, November 13th. A couple things to note. These black lines, this is the surface pressure. Nothing may initially stand out at you, but you see how this buckles? there actually is a subtle wave of low pressure in here. And when you look at this further, these green shading, this is where the higher dew points are. So the light green indicates dew points over 40. Then you see 45, 50 plus. Now, if you picture a low, say just on the Connecticut-Rhode Island border, that counterclockwise circulation, you're going to be pulling south winds up to the east of that. And you see that higher dew point coming up. Obviously, 50 dew points is not that much, but we had certain conditions that were met elsewhere in the environment to kind of compensate for that. One was those very strong wind fields we saw at 500 millibars. So another tool that we utilize is just looking at the significant tornado parameter. Again, this is just an indice. It doesn't tell you there's going to be tornadoes. Many times this is lit up. In fact, most of the time when it's lit up, nothing happens, which is very fortunate. But it's just a little identifier. Do you see that's lit up? Well, in New England, it's probably lit up maybe a handful of days, not more than a dozen days a year. So if that's lit up, even if you're not thinking tornadoes, maybe you start to put in the back of your mind, well, there's enough turning of the winds in, say, the low levels, that maybe there'll be a low risk. So again, it's bringing that situational awareness into the forecaster. So that's why all these individual parameters are really important to look at. They don't give you the forecast, but they give you, say, a possibility of something happening. And then you kind of put all the pieces of the puzzle together, and that can really allow you to put together a very good forecast. So another tool from the HREF. Now this may look like a messy coloring by, say, a 5-year-old, but what this is actually an indication of where reflectivity on the radar is simulated to be over 40 dBz in returns, which sometimes can be indicative of very heavy showers or thunderstorms, coupled with instability. Now, this is modest instability, actually fairly low instability, over 50 joules per kilogram. That's not a lot, but remember, you're combining those two things. So if you have just a little bit of instability and pretty impressive returns on radar, that's going to indicate the potential for some thunderstorms. And you can see where the model focused, where you see everything's kind of overlapped from all the individual members of the ensemble, generally south of the Pike, Connecticut, Rhode Island coast. Again, as you get north of the Pike, you see it becomes more sporadic. It's telling you, well, there are some members forecasting thunder, but the greatest risk is south of the Pike. So again, we're putting everything together, building that cake, putting the pieces of the puzzle together. Okay, so now we are on to another parameter from the HREF. We are looking at a parameter called updraft helicity in a 2 to 5 kilometer layer of the atmosphere. What this tells you is that there is rotation in that portion of the atmosphere, and that it can be conducive for thunderstorms, perhaps with strong winds, perhaps if conditions are right, a tornado. Notice where you have these little circles there, those dark brown circles. That is where the model is indicating that updraft helicity at 21Z. Notice to the right of that, you see this gray shading. Well, that is where the model is indicating most unstable cape. So you've got not a lot, but it's indicating, say, 500 joules per kilogram of most unstable cape working its way up to the coast. So there you have two things. The model's telling you there's good spin in the atmosphere in the mid-levels, and you have just enough instability coming in. Now, again, if this was summer, it'd be hardly anything, but you wouldn't have the extreme wind fields that we have this time of year. So again, the wind can compensate for the lack of instability. And sometimes in the summer, it's the opposite. You don't have much wind, but you have tremendous instability, which compensates for the wind. So it's all a balance. Okay, this is yet another tool. What this is, it's where you have the velocity, the wind speed, over 30 knots, coupled with radar return, say over 20 dBz, which isn't that strong, but it's telling you that convection, or thunderstorms, I should say, may coincide with that strong wind. Now, keep in mind, you see the shading is over the ocean. This is, a 10-meter wind. So a lot of this may stay up above the ground. It may never be felt at the surface. And that's why the model prints most of it out over the ocean, because there's less friction, so there's a better chance of the wind getting down to the ground. But you'll notice there's these little green shadings just off the coast, inside Long Island Sound there, just south of our land areas, where you're seeing pockets of wind gusts over 50 knots. So again, it's not telling you that's going to necessarily happen, but it's another signal there. Again, we're putting everything together, and the more we look at, you're starting to see all these little individual parameters start to come together, and things are becoming more concerning. So now we're going to get into the mesoanalysis. We're looking at the actual conditions during the hour leading up to those tornadoes. And again, what you'll notice is what the HREF showed us at 500 millibars, a very potent trough, shortwave trough coming into the area. Out ahead of it, you have tremendous wind fields over 100 knots at 500 millibars. And we had a student work with Joe several years back, a student volunteer, do a study in what is the upper level features when we do get, say, tornadoes in New England. And notice you have on here that upper trough coming down into the Great Lakes. But keep in mind, most of those type of troughs aren't going to be as dynamic as this one, because a lot of them are, during our typical thunderstorm season. So in this case, you're going to be dealing with stronger wind fields. But the idea is pretty much the same. That trough axis is approaching our area from the west. So this was a look at the station observations at 5 p.m. on the evening of November 13th. So, just taking a close look at it, it looks like Worcester is 51 over 40 with some showers. Fitchburg is 55 over 33. It looks like there's some dry air. The Pike, looks like Pittsfield's about 36 over 34. Looks like they're about to mix with some snow. You do see a thunderstorm at Westfield. But let's look to the area concerned. Providence is 56 over 43. Willimantic is 46 over 45. Newport is 56 over 47. Doesn't really seem concerning, and doesn't certainly look like thunderstorms, let alone tornadoes. So this is an example. We need to dig deeper. We just looked at all that model data from the HREF that was pointing us in certain direction. So let's take a deeper look at this. Okay, what we see here, remember we saw that little surface wave, what we call a meso low on the HREF, where you had those dew points coming up. Look at Block Island down here, 58 over 55. And with a strong southerly wind. Then just northeast of the surface low, Providence, 56 over 43, dew point with an southeast wind. Willimantic, 46 degrees. They're on the west side of it. Look at that. You see a little circulation here. So that is typically a big ingredient in getting these tornadoes in this type of environment, having a meso low to enhance that low level helicity and also bring up higher dew points. You see that it's a very narrow corridor, but 50 plus dew points were surging northward just ahead of this surface low. And we're going to talk about the warm sea surface temperatures. What's interesting, this is comparing the sea surface temperatures to what they normally are for this time of year. Basically, they were 2 to 4 degrees Celsius above normal. So we usually look at the ocean as a deterrent for thunderstorms and severe weather, right? How many times April, May, June, July have a line of thunderstorms approaching the Boston and Providence corridor? It looks really impressive. And then you're lucky to get 2 drops of rain once it gets into far southeast Massachusetts. The whole thing falls apart as it runs into the cold ocean. Well, there are cases where the ocean can actually help, especially in the fall season, if you have enough instability, because the ocean is still relatively warm. So you can actually bring in higher dew points off the ocean, particularly when it's running so much warmer than normal. And if you increase the temperature by a couple degrees, you increase the amount of instability. But if you increase the dew point, the moisture, by a couple of degrees, you increase the instability exponentially. So that can make a huge difference from just, say, run-of-the-mill showers to thunderstorms with strong winds and a couple tornadoes. So it's these subtle things that make a big difference in the outcome. So we talked about at the beginning of this presentation surface instability CAPE, convective available potential energy. This was the CAPE depicted at 5 p.m., right around the time of the tornadoes. And you see this subtle pink shading, 250 joules, just limping onto the south coast. To be honest, that is very little CAPE. Looking at this, you really wouldn't think of even any thunderstorms. It's not something that would stand out to a forecaster. So again, another example of needing to dig deeper, and that HREF model, those ensembles really hinted at that. We needed to dig deeper. Well, there's something called the 0 to 3 kilometer CAPE. That is looking at the CAPE in the lower portion of the atmosphere. And a lot of studies have been done on that low level CAPE, and they indicate that tornadoes usually occur when the 0 to 3 kilometer CAPE is relatively high, say over 50 to 75 joules per kilogram. That's actually very high low level CAPE. And not only does the risk for tornadoes increase, but severe weather in itself increases. So even though the overall instability was rather low, the most important CAPE, that low level CAPE, was very modest, very moderate at the least. And again, when you're doing these analysis, we don't look at, oh, well, there's 25, 50 joules right to the Rhode Island coast. I don't think that's enough. We're going to need 75 to 100. Well, when you see these tight gradients, this was taken at the top of the hour. In reality, it may be 100 joules. You may have a very narrow corridor of moisture that this mesoanalysis isn't going to be able to pick up. But the idea is, if you see a tight gradient sitting nearby, we may have had over 100 joules per kilogram of 0 to 3 kilometer during those tornadoes. I think we probably did. And that is actually very high CAPE. So even though the overall CAPE was low, the important CAPE in that low levels was probably pretty high. Another key factor are the 700 to 500 millibar lapse rates. Most of the time in our region, our lapse rates are usually 6 Celsius per kilometer or less in that layer. In this case, they were 6.5 to 7.5. And the big thing, what we as forecasters tend to look at for overall severe weather, if you have strong winds aloft coupled with steep mid-level lapse rates and just enough instability, that's usually a red flag that, hey, thunderstorms are a decent bet and they may overperform. They may produce, higher end impacts than what initially you might be thinking. And believe it or not, we've actually had thunderstorms tonight across New York State into Albany's area. They're just kind of working towards western Massachusetts, even though, temperatures aren't that mild. Well, they're mild for where they should be this time of year, but they're upper 40s to mid 50s. Our mid-level lapse rates right now are around 7 Celsius per kilometer. So that is a very important factor in thunderstorms. And again, we talked about needing that upper support, especially when you're dealing with low overall CAPE. Well, we had 60 to 80 knots a shear. Typically in the summertime, we're looking at, for severe weather, you like to see at least 25, 30 knots. And sometimes 35, 40 knots would be really impressive. But now we've got 60 to 80 knots. So that's indicative of that very strong shortwave, that strong upper dynamics that you get in the fall season. And most importantly, that low-level helicity, that 0 to 1 kilometer layer, how much turning of the wind is in that layer. And that's what that meso low does, because we saw how the winds kind of rotate counterclockwise around low pressure. Well, just east of that meso low, you can have, tremendous turning. And we usually look for values over 100. In this case, you can see they're over 200, right in the area where we had the tornadoes at the time. So again, there's so many tools that we can utilize to really, really help us forecast these events. Plus, we had the, low-level instability, the shear, and combine that with the steep mid-level lapse rates. It's not really surprising what took place. So with that, I am going to turn it over to Rodney, and he's really going to go into detail of the radar event, the signatures he saw, because he was on the hot seat that afternoon and evening working the radar. So Rodney, are you ready to go?
Yes, Hayden, thank you so much. Well, good evening, everyone. So yeah, it was, like Hayden said, it was a pretty crazy event. It's a very late season, a severe type of situation. And just taking a look at the radar loop, you can see basically the storm system was flying, and was basically kind of like an all hands on deck situation. And you can see how the warnings just kind of blossom as that line of storms. And this is what we call a QLCS, quasi-linear convective system. You can kind of see it is kind of like a straight line, but it also has like bulges in the line. And those are the bulges are the type of things that the warning meteorologists would look for potential areas of where you can have a brief spin up or actual tornado touchdown. And that was actually what happened across basically started in Long Island in New York State, and then kind of migrated along the Connecticut coast and then into Rhode Island. Okay, so as I have mentioned previously, QLCS tornado, and this is basically like the kind of taking a deeper look at what we mean by QLCS tornadoes. So, we might be, some of us, who love tornadoes or severe weather. I myself, I went to University of Kansas, and I've seen, like those really impressive, like Central Plains or Tornado Alley type of supercell, and then you have those very photogenic tornadoes. Of course, you have to look at them from afar. You don't want to get too near to them. But in New England, usually, we do get supercell environment from time to time. Like for example, the Worcester tornado, a few years ago, and but most of the time we get this QLCS setup where there are short-lived spin-ups that again form along the line of thunderstorms, and where you have bulges, and those are basically kind of weakness in the line, if you like, and notice where focus on the areas that are in the circle. And so, for example, you compare that as the reflectivity, and then you compare the velocity. You kind of can make out like a couplet. And of course, not all velocity couplets are indicative of a tornado. You kind of have to compare it with what we call correlation coefficient, and where you see kind of like a drop in the CC, that might be indicative of some debris being lofted into the atmosphere. And so usually the recommended warning strategy, as Joe would say, our science and operations officer, would be a severe thunderstorm warning with a tornado possible tag, because sometimes in this kind of situations, especially a potential complicating factor was that at that point there were a lot of leaves on the ground, or maybe just the leaves on the trees but barely hanging on, and you have strong straight line winds, and you could basically, the radar could just be picking up what I call leaf NATO, so just basically like leaves spinning around, and and that's actually not an actual tornado. So it's a very kind of complicated situation whereby you kind of have to have a very delicate balance between, is it going to be a false alarm, or you also don't want to run the risk of not warning an actual tornado in a densely populated area. So these are some of the dilemmas that we as warning forecasters we run into. But usually the recommended strategy again is severe thunderstorm warning with a tornado possible tag. And again, these are more diagrams about and I will not go into too much details. You can after this presentation, you can, if you have more questions, you can feel free to email Joe, or go to our YouTube page and Google these terms, like for example rear inflow notch. I talked a lot about the line break, and those couplers, basically those are mesovortex, and another key signature I want to briefly talk about is what we call the rear inflow jet. Basically, think of the thunderstorm as like a living organism. You need to give it nutrition for it to flourish or blossom. So in this case, you kind of need like an energy source, in this case through the rear inflow jet, and that is usually seen on the reflectivity. In this case, 0.5 degrees. You will see kind of an area of low reflectivity, so indicated by the green. Those are yellow and reds. There's a higher reflectivity associated with heavier rainfall. But yeah, once you see that drop in reflectivity, you have to be cognizant of the existence of a rear inflow jet, and that is usually kind of like one of the telltale signs that that storm could become nasty. And then you also have that contracting book and vortex at the bottom center. So again, you kind of just have to we learn some of this in radar school and some of them through online modules, but a lot of times you just have to work through this kind of event. And people like Hayden, Joe, I mean, they've been like in the business for so long, and for them it comes second nature to them. For me, I'm a newer meteorologist, so I have to get more experience. And unfortunately, sometimes you will make mistakes, and not through the lack of effort, but that's how you learn.
And Rodney, don't feel bad, because even though Hayden and I work all these, this is probably the most challenging to do. So it never gets easy, put it that way.
Yeah, I don't care how much experience you have. Those signatures were extremely difficult that day.
Okay, thank you, Joe and Hayden. So and the day after the event, was we have storm survey team went out, to survey, and we actually also have to coordinate with our neighbors in New York City, and because they were also doing storm surveys, and obviously they had all the damage in Long Island into coastal Connecticut. So there was a lot of collaboration going on behind the scenes, and and also all thanks to our emergency managers and you, the public, for giving us the great valuable information on social media or calling in on the phone, and we really appreciate all your help, sincerely. And this first damage survey report is from Windham County, Connecticut into Rhode Island, and you can see it was on the ground for just under 15 minutes and given an EF0 rating with peak winds of 80 miles per hour, path length 6 miles. Thankfully, no injuries or fatalities. And here's taking a look at, we usually like to look at this, what we call the 4-panel. And the advantage of this 4-panel is that you can have the reflectivity on the top left, velocity top right, and you can see that, correlation coefficient on the bottom right corner, and that was the differential let's see, what is that? Differential reflectivity, no, ZDR. Usually sometimes I blank on the real name of the acronyms. But so when you put all of them together, it increases the confidence that there is maybe a tornado on the ground. In this, and especially it's a very rapidly changing kind of situation. The signature may not be very clear cut. You need all the evidence that you can get to increase your confidence to the extent you put out a warning. The second report, that's Stonington, Connecticut into Westerly, Rhode Island. And Stonington is in the New York City Forecast Office area. And so this is, one of the situations where you actually have to coordinate the storm survey and come up with like a joint storm survey report. And this was actually an EF1. I believe there was a barn that was just destroyed. And the EF rating, for those of you who are not familiar with it, it's kind of like the equivalent of the hurricane categories, but in this case, tornadoes. Damage is the main consideration, and as well as the estimated peak wind. So this one was, was shorter, but it was also a little bit more destructive, but thankfully no injuries. And here's taking a look at that EF1 tornado, and this, you would take a look at this, and it's actually not that clear cut. That's actually a tornado on the ground. And you can see the commentary on the left-hand side. You couldn't actually see the circulation well enough due to what we call the de-aliasing. But the lowest CC correlation coefficient on the bottom right corner, and as well as the reflectivity signature, those are kind of clues. But then again, because there was a very fast-moving line, and there might actually be several bulges in the line. So it's a situation, and this one I believe it was actually we didn't actually warn on it, but yeah, you can see why this could be so difficult in this kind of situation. And so we also have the North Kingstown, Rhode Island tornado, and it was on the ground for 6 minutes. EF0. Again, thankfully, no injuries or fatalities. And so this was the that EF0 tornado, and it was kind of like just inside the tornado warning polygon. And this, some of you might remember that day actually there was the 2 tornado warnings issued, and you can see this in this case, the weak circulation and lower CC are kind of the clues after the line bowed out. And this is going to Martha's Vineyard and on the Massachusetts side, and so we issued a tornado warning as well for the Vineyard, and was the day after Nantucket got their first tornado warning in ages, and so one for each island. So so there was a possible water spout, and approaching the Vineyard, and usually, and at that time for the mariners there was actually a special marine warning, and we warned them of the potential for water spouts. But in this case, this potential water spout was a little bit too close for comfort, and that's why that was the main reason we went with a tornado warning for the Vineyard and actually into parts of Buzzards Bay. So you can see a kind of like the nice velocity couplet, but when you take a closer look at the correlation coefficient, it's actually not that clear cut. So in this case, this was a situation whereby, obviously the water spout was over the water. There is no debris over the water, so you're not going to pick up on that lower correlation coefficient, unlike over land. You have all kinds of things like tree branches, etc. And so, that's why this is a situation whereby, you kind of have to use a use a judgment call, and potential water spout, if it comes on land, it becomes a tornado. So that's why we went with the tornado warning.
Yeah, Rodney, I'll just jump in and mention, I thought this was a really good warning, actually. You had this tight couplet here, and like you said, you're not going to see much in the CC over water, but it's in the right spot. And you knew there was a history as well with this line. It was producing tornadoes, and I think you also knew the environment that Hayden had mentioned and gone through. So in the warning process, for everyone who doesn't know, it's not just looking at radar signatures and reacting. It's kind of knowing the environment, knowing the history. And when you see something like this, then you try to anticipate it a little bit. So, definitely great job on this, Rodney. I think it certainly was warranted here. Even though on the next slide, which I'll go to, it didn't exactly pan out. So I'll let you take it from there. But still some high winds on the island.
Yeah, thank you, Joe. Yeah, I think the wind had picked up like a 50-knot wind gust at the airport, and so yeah, it was for those of you who live on the vineyard or have friends who live there, they definitely had some very windy moments. But it was a case whereby sometimes just by a stroke of luck, you issued the warning, it looked great, and then it weakened. And I believe that was also what happened the previous day for Nantucket as well. It was a potential water spout, but then weakened as it approached land. So, what can you do? So, and like I said, there was a report of, in this case, actually 69-mile-per-hour wind gusts in Edgartown as the line moved through. So other tornadoes for Southern Connecticut and Long Island, that's actually in the New York City office area, but we will cover them as well. So, and this was actually in Connecticut, and again, so weak circulation. If you look at the reflectivity, you wouldn't think this is a tornado, but there was a kind of a velocity couplet. And for those of you who are not familiar with the velocity product, green means inbound towards the radar, red means outbound. So if you have the green and red next to each other, there's a circulation. And so there's actually a kind of like a lower CC evident in the bottom right corner. And so, putting it all together, again, slim pickings, but you can see that there's a weak bow in the reflectivity.
Yeah, and Rodney, I'll just point out, this is from the New York radar. So we're probably almost 4,000 feet up here. So I think we're probably missing the true circulation down right near the ground. But you can kind of see, if you use your imagination, there's a little bit of a bow there. So yeah, not an easy call. This one too.
Yeah, so this one's in Branford, Connecticut. Again, and a lot of times these are low top thunderstorms, and that's why I say, I went through the radar school, and the Storm Prediction Center is based in Oklahoma. They are more used to those very tall supercells, and these are low tops, and sometimes the radar actually might be overshooting the top of the clouds. So you have to kind of use for situations like this, you have to look at other radars, and in this case, it might be the New York City office radar, it could be Albany's radar, or even like the Boston terminal radar, to what we call the T-BOS, and especially that radar is actually very good for areas around the Boston area and Metro West, but you kind of have to use all of the resources, be creative in this kind of situations. And in this case, again, the reflectivity doesn't show much, but you can make up the velocity couplet, and that this might be a little bit too high for than what you prefer. But again, you have to deal with the limitations. But you can see that CC drop, which actually may have been the leaves swirling, and given that there's so many leaves on the ground. And this one is actually an EF1 in New York State. And when you look at that velocity couplet, that's actually a telltale sign. That's the blues are actually higher inbound wind than the greens. So in this case, you see the bright red and the bright blue color side by side. That's actually very good rotational velocity. And for those of you who are curious, we calculate rotational velocity by taking the average of inbound and outbound wind. So if your inbound and outbound winds are higher, your average is also higher. So and you see a very good CC drop there. So that increases the confidence that the bow and the reflectivity, that's actually a tornado on the ground. And so the New York City office went with the tornado warning. And like Hayden mentioned, 100 miles away, 150 miles away, it's actually snowing. And I believe there was like a report of thunder snow too. So just crazy day of weather. So in summary, the QLCS featuring a low Cape, high shear environment spawned the formation of 11 tornadoes across Connecticut, Rhode Island, and on Long Island. Even though there's a lack of near surface moisture, the dew points were in the low 40s. Typically you don't think about severe weather when dew points are so low, but the dynamics are just so impressive. It overcame the lack of moisture. And when you have low top environment, you have to look closely at the 0 to 3 kilometers Cape or instability, as well as the 0 to 1 kilometer shear, which is the kind of directional and velocity difference with in the wind speed at different altitude. And so warning with lead time for this type of tornadoes, given that they are moving so quickly, is extremely challenging. So that's why it's very important to know the near storm environment. The warning team correctly used VCP 212 with Sales tool. Basically means that the radar is working over time. And in hindsight, maybe we could have gone with Sales 3, which the radar would be spinning very quickly. And best practice, is to issue severe thunderstorm warnings with the tornado possible tag, unless we know with high confidence that there's actually an actual tornado on the ground. And that's when your reports are so useful, and so and with that, I think I'm going to talk briefly about the WRF simulations that one of our meteorologists, Bill Leatham, actually he ran this WRF model at home. And basically what you're seeing here is that the center image is the control run. So assuming that all the conditions are unchanged, then that's actually what how storms might spin up. And so the cool run is assuming the sea surface temperature is cooler, and the warm run assuming the sea surface temperature is warmer. And for those of you who follow the kind of like the marine side of things, we had a very warm fall, and the sea surface temperature, unsurprisingly, is running kind of above average. And while it is, it's only a theory, but the warmer sea surface temperature could have played a role in the more robust storms this late in the year. And again, control run is in the middle, cool run on the left, warm run on the right. You can see that the storms are a little bit more feisty and more robust with assuming warmer sea surface temperature. And taking a look at the mode of sounding, so you can see that in this case, you have the warm run on the right-hand side, cool run on the left-hand side. So basically, might be a little bit overwhelming, but basically you have, the Cape, 0 to 3 kilometer Cape is actually a little bit more on the warm run. So usually when you have warmer sea surface temperature or near surface temperature, you get more instability. And in this case, we focus on the 0 to 3 kilometer because all this is low top. And the lapse rate is also a little bit higher. So usually we want lapse rates that are above 7 Celsius per kilometer. In this case, you have 8 Celsius per kilometer, so very good. And also a little bit higher mid-level lapse rate.
And Rodney, the other thing that Bill Leatham had mentioned when he ran this was if you look at the analog on the sounding, on the cool sounding, there's really nothing. But look on the warmer one, which I think is probably more reality, marginal tornado. And if you look at the line, it actually gives you EF0, EF1 tornado potential. So that kind of worked out. That's pretty cool. And I think, Rodney, remind me, I think he just tweaked the sea surface temperature by like 1 degree Celsius either side.
Yeah,
Yeah, so I mean, it wasn't like Hayden mentioned, 1 degree Celsius warmer made all the difference in the world. So that's very, very subtle. Not something we can easily predict ahead of time.
Yeah, thank you, Joe. So yeah, continuing with the summary, 11 tornadoes touched down in the area. So warm sea surface temperature likely played a role with boosting the low-level instability along the coast, and this was supported by the WRF model run by Bill Leatham. And snow was falling, and with even a report of thunder snow across the higher terrain of Western Mass, while tornado warnings were ongoing across Rhode Island and Eastern Mass. And the last time I remember this was happening was when I was in Kansas, so when they had a blizzard in Western Kansas and tornado warnings in across central Kansas. So this was almost like kind of like a wild weather day in the center of the country. And with that, thank you so much for listening, and we'll pass it back to Joe.
All right, so Rodney, we can pretty much blame you then. You brought it here from Kansas. Okay, thanks. Yeah. All right, so I know Hayden is still with us. Let's see. Go through some questions. From Carrie, are lifted indices as big a factor in our tornadoes as for the plains? If they were, what were the lifted indices for this event? That's kind of an older method that's been used that shows instability, Carrie. It's just one. Nowadays, we look more at that cape that Hayden showed for instability. That's good pretty much. I like to use that, and Hayden, Rodney, feel free to chime in. I like to use that for the wintertime, actually. And Carrie, I think we talked about having a thunder snow webinar, which we're going to be working on for January or February. But Hayden, do you use that much? Because I don't think we do as much as we used to.
Yeah, I mean, I utilize it, but to me, it's just another tool. So one thing the lifted index can tell you is if you have fat or skinny type cape, and that's kind of similar to looking at the 0 to 3 kilometer cape in certain aspects, but it doesn't tell you the location of it. But there is some utility to it still, because you can have, say, 1,000 joules of cape, but it could be the thin cape or the fat cape, and the fat cape is much more useful for strong to severe thunderstorms, and you get that by utilizing the sounding. But overall, the 0 to 3 kilometer cape is really, I think, key, and Joe mentioned that too, in what we're utilizing now, especially for these tornadic type events.
Yeah, I remember. I mean, Hayden, probably in our earlier days, we used lifted index all the time, and you didn't really use cape at all. But now the science has kind of evolved a little bit, where it's a much better indicator. But Carrie, we're going to talk about lifted index when we get into our thunder snow webinar coming up in the winter. So stay tuned for that, because it is used in that situation. Comment from Ronald, and I know he had emailed me about this. He's in North Kingstown, was affected by the tornado coming from westerly. The path was 4 streets down from his apartment. Didn't receive a warning on NOAA or the radio due to how fast the cell produced a tornado. Lucky just to his south, heading into Wickford. So yeah, Ronald, that was I'm sure quite an experience for you. Question from Ethan. I'll throw this one to Hayden since it has to do with the HREF. For the 10-meter wind speed product, does it refer to the sustained non-precipitation wind or any sustained wind at the surface 10 meters, regardless of the cause?
Yeah, so there's a couple choices you have when you're looking at the HREF model. I believe the example I showed was where you were combining, and it's not supposed to be a gust, it's just a general wind, but it's a relatively large area, 10 meters. I had chosen a parameter where you overlaid it with 20 dBz returns, so you'd be kind of incorporating where you had stuff on radar where with the wind. But you can look at it. There are a couple different ways where you, I believe, can just look at the wind output. Depending on, I think this goes back to the importance of looking at the sounding, because you have to kind of defer how well the atmosphere is going to be mixed, because a lot of times that wind can stay aloft. It may not come down to the actual surface. So in this case, the soundings, everything was well mixed. Temperature was decreasing with height fairly rapidly. So when you have that type of setup, that can bring wind down to the ground. But that goes into kind of the mesoanalysis aspect of the event and events themselves, and the need to analyze that, not just take the 10-meter wind verbatim.
Right. Okay. Thanks, Hayden. Let's see. I'm just going to go through a few more here, and if I don't get to your question, you can feel free to shoot me an email too. We've got a bunch in here. Let's see. Question about the resolution of SPC's mesoanalysis. How smoothed out is it? It actually, Ethan, is. It's, I believe, Hayden, is it 12 kilometers, 13 kilometers? It's not that high a resolution.
Yeah,
it's based on the RAP model, actually. That's the background.
Yeah, I don't know the exact number per se, and that's kind of why also we look at the gradient of where those parameters are. You don't have to be in the highest value, but near the gradient, because it may be higher. And I think with that mesoanalysis, even more important than the specific resolution is the data that's going into the model. And if there's tend to be less data available coming off the ocean as from the land. So when you have southerly winds like that, you could run the model at 1 kilometer if you wanted to, or the analysis at 1 kilometer. If you don't have the data points, it's not really going to give you a more accurate forecast. So, or analysis, I should say, whatever you're trying to get out of the model or analysis. So I think that's a limiting factor, is the amount of data. I mean, it's a lot better than we used to have, because the models with the infrared imagery of the clouds, radar, all that stuff gets thrown into the analysis, but it's still not as good as having all the data on land, especially for an event like that.
Yeah, and what you're seeing is it's a 1 hour forecast from the RAP, which is kind of the background, and then all of that observational data is superimposed on top. So it's not perfect, but it's a pretty good guess of what's going on. So good question. Okay, from John, what drove the high mid-level lapse rates? And Hayden, to me, it was just you had that trough with the cold air aloft, and just enough warming at the surface in that point. You see anything else?
Yeah, I think you nailed it, Joe. I mean, that when a lot of times I'll tend to look at what are the 500 temperatures compared to the 700 temperatures, but a lot of times you can just overlay a 500 millibar temperature map, and sometimes you'll actually see a bullseye of, say, like minus 25, 500 minus 25 Celsius, 500 millibar temperatures moving across the area. That's usually like right where the shortwave is located, and under there you're going to have the steepest lapse rates. So there's a lot of different ways you can analyze what the mid-level lapse rates are, but we're usually looking for that cold pool loft right around 500, 600 millibars.
Right. Okay, here's a question, Hayden, from Tom, and this is talking about the mesolow. Probably, more or less how does it form, but can the latent heat release be important in these mesolows? And we're talking about a storm scale, very small scale feature, but go ahead.
Yeah, exactly, and that's the tricky point about those meso lows. I mean, they're just basically a surface low, but on a very small scale, and that's why whatever resolution you can run a model or analysis down to, you could run it at any level you want. You could run it a quarter kilometer, but there's only a certain amount of data that's going to be able to analyze. And keep in mind, like when you get, say, a storm, your low-level helicity may be analyzed at, say, 100 at 0 to 1 kilometer. but say within a quarter mile of the storm, you may have really strong east winds just in that very, very narrow path. So instead of a mesoscale, it's a micro scale. You may actually have helicity values of 300-400. There's just no way to measure that. It's just something that you have to keep in mind, and that's why sometimes those parameters may not indicate the potential for a tornado even right at that time it's occurring, is because there's only so much data to work with. And when you're talking about meso to micro scale, we're just not able to see those features yet. Even we kind of know they're there. We really know when you're within, say, a half mile of a thunderstorm, probably the instability and the helicity is a lot higher than we're able to analyze. But we keep that in the back of our minds.
All right, so let's see. A couple more questions. This is from Tom. Over the North Shore, lightning was really infrequent and diffuse. He was asking about the freezing level, but I think, Tom, it had more to do with the fact it outran the instability, the line, as it moved into eastern Mass. Remember, all that, what Hayden showed was over Connecticut and coastal, Rhode Island and south coastal Mass. So by the time that line reached eastern Massachusetts, greater Boston, it had really outrun the instability. It was kind of starting to fall apart a little bit at that point. So
yeah, if you remember,
yep.
Joe, from that HREF imagery where we had the 40 dBz return from the radar, overlaid with all the models where you had MU Cape, that most unstable Cape of over 50 joules, you saw that tremendous clustering south of the Massachusetts Turnpike, and then you still saw it north of the Massachusetts Pike, but at a more sporadic plots there, because you didn't have the instability. The instability was all south of the Pike.
Right. Yeah, good point. And we'll just see from John here. He wants to know, would phased array radar have been able to produce more convincing velocity couplets? Good question. I would say maybe. I think the problem with this wasn't the fact that we're using Doppler radar. It's the fact where the Doppler radars were located. We're sampling Connecticut, western part of Rhode Island, again, 4,000 feet up. And these circulations were so shallow, they probably weren't much more than a couple thousand feet. So we're sampling the very top, scraping the top of that. If there was a radar, say, in Westerly or in that area, we probably would have seen a little bit more. So phased array radar is a little bit different than the radars that we have now, where it's a dish that's spinning. It doesn't have any moving parts. So that's something that the Weather Service is looking into, and probably Hayden, I'm thinking the earliest prototypes are sometime in the 2025 and beyond, depending on funding.
Yeah, I think it's going to be
it's a while. Yeah. But to say, I think it was more of just a radar coverage sampling problem more than the type of radar, John, if that makes sense. So, if we had more radars, I think we would have had a better, sampling there. But, that's just kind of the way it is, that we can only have so many in the area there. And I'll do one more here from John. Just wanted to know, and Hayden, you may remember this, how well the HRRR, the High Resolution Rapid Refresh Model, do for this event? Do you recall, or Rodney?
Yeah, so I mean, I can recall that, like, even there's runs now of the HRRR that go out 48 hours at 0, 6, 12, and 18Z. And I remember even the 48-hour HRRR had like a line of, convection kind of lifting, eastward with that cold pool loft. So, it did fairly well. All the models did fairly well with the simulations, indicating a line of, low top thunderstorms. I think it was just putting together, well, we're just going to be, low top thunderstorms with 30 to 40 mile per hour wind gusts and pea hail, or were they going to be, 50 to 60 mile per hour gusts with, a bunch of EF0, EF1 tornadoes associated with them. So, there's a lot that the radar simulations can tell you from the model radar simulations can tell you, but there's also a lot they don't tell you. Give you an idea, but again, that's why it's kind of important to go through all those parameters that we did you have to put all the pieces together. And then once you do that, you kind of see if it fits into a puzzle. And I think there's obviously a reason why this event happened. They don't happen out of the blue, because we had so many of those things coming together.